In this lecture, we will discuss the formal definition of an algorithm.
In the last lecture, we just informally defined what algorithms are. So let's now give a formal definition of an algorithm. So what is it? It's a well-ordered collection of unambiguous and effectively computable operations that, when executed, produces a result and halts in a finite amount of time. What? Okay, so there's our formal definition. So let's kind of break this definition down into parts, since this seems like a very long definition. So we'll just break it into smaller parts to help you understand what this definition is saying. The first part of the definition says that we have a well-ordered collection. So an algorithm is simply a collection of operations. That's what it is. And we must be clear and unambiguous with the ordering to these operations. So that means we need to know which operation to do first, and then what's the next operation, and then what's the next operation after that. So I mean, our operations need to be clear, and there should be no reason to guess what the ordering is. So we can't let the computer guess what to do. Computers can't guess. It can do some randomization, but that's not the same thing as guessing. We do not want to make the computer try to guess what the next step is. We need to make it very clear what the current step is saying to do, and then what the next step is, or where to go to do the next step. Let's take a look at a bottle of shampoo as an example of ambiguous ordering to our operations. So if you take a look at the back of any shampoo bottle, they usually have the same set of instructions or directions. They'll say to wet the hair, lather, rinse, and then repeat. Okay, well, that's great. So we know we need to wet our hair, we need to know the lather, to rinse, and repeat. But we can guess that we would repeat steps 2 through 4, but the instructions aren't clear about that. So after we rinse, do we wet our hair again? I mean, it's already wet, but we would guess that, well, maybe we can just skip that step and we just lather again, and then we would rinse it. It also doesn't tell us when to actually stop. So I think there was a comedian out there that even talked about this, that they said that there are some people that could still be in the shower just lathering, rinsing, and repeating, because it doesn't say to stop, it just says repeat. Repeat until what? Until you're happy with your hair? Or do you repeat 5 times? But it's not clear when to actually stop lathering and rinsing your hair. So what we saw in the last example is that if we have ambiguous instructions, it can leave us confused or unsure about what operation we need to do next. So it's important that we're very precise about our instructions, making it clear on what step we need to do and what the order of those steps are. One way we can go about doing this is by numbering the steps of our algorithm. We saw this in the adding example from the last lecture where we add 2 numbers. We actually had step 1, step 2, 3, all the way up to like 9, if I remember correctly. So we can use these numbers to specify the order of our instructions. Let's take a look at some examples of ambiguous and unambiguous statements. That way we can see how numbers can be used to help give us an order and more precise steps for our algorithms. So an ambiguous instruction would be go back and do it again. Okay, so go back where? We don't know where we're going to go back. And then when we say do it again, what part do we do again? There could be a specific step that we repeat, or maybe there are several steps that we're going to repeat, but we don't know which ones we're going to do. So something that's a little bit more precise, more unambiguous would be go back to step 3 and continue execution from that point. This is more detailed. It gives us very clear details on what we're supposed to do. And another example of an ambiguous statement would be to start over. Okay, start over from where? We can assume that we would start over from the beginning, but once again, we've talked before, we don't want to have the computer try to guess something. We can't assume that if we're starting over that we start over from the beginning. Something that's a little bit more precise would be start over from step 1. That way we know exactly which step we're going to start from. Another ambiguous example would be if you understand the material, you may skip ahead. Well, skip ahead to where? Do we skip ahead to the portion that until we don't understand it? I mean, there's no clear indication of where do we actually skip to. So something more precise would be if you understand the material, skip ahead to line 21. And that would Tell us exactly where we're going to go if we understand the material. And then another example would be do either part 1 or part 2. Okay, when do we decide to do part 1 or part 2? Do I just randomly pick one and say, oh, I just feel like doing part 1 today, or I feel like doing part 2 today? When should I do part 1? When should I do part 2? So here's something a little bit more precise. If you're 18 years old or older, do part 1 beginning with step 9. Otherwise, do part 2 beginning with step 40. So here we have very clear details, a clear indication of when you do part 1, when you do part 2, and exactly where do you actually start in those set of steps.